So what's up, everybody? How are y'all? Good. Awesome. So last class we left off with this problem B here. I don't remember if we did C, but let's look at that really quick for just a second. So we can think of this in terms of the general power rule, or we can think of this as U substitution. Since the general power rule is a particular case of U sub, let's think of it in terms of U sub. What we've got is 3x squared, the square root of x cubed minus 2 dx. Now, to do this problem, let's start by rewriting this entire integral so that the square root is a power. 3x squared, the quantity, x cubed minus 2, all raised to the 1/2 power, dx. Now, if we look at this, you might notice something, that what's outside of the parentheses is the derivative of what's inside the parentheses, right? So using that, why don't we say u is equal to x cubed minus 2, then du dx would be equal to 3x squared, and du would be equal to 3x squared dx. So by subbing in this u, this is going to turn into the integral of u to the 1/2 power du. All we're doing here is we're rewriting x cubed minus 2 as u, and then using that information to rewrite the rest of our integral. Make sense? So since what we get with u sub is u to the 1/2, we can integrate this using just a simple power rule, right? So simple power rule tells us that this comes out to be 1 over 1/2 plus 1 times u to the 1/2 plus 1, all of that plus c. Well, we can rewrite this now. Rewriting this, starting with a fraction, this is going to come out to be 2 over 3 u to the 3 over 2 plus c. So when we substitute u back in, so we're going to now plug in x cubed minus 2 back into u. What we get is 2 over 3 x cubed minus 2 raised to the 3 over 2 plus a constant. So having said that, we can check our work just by taking the derivative of this and checking to make sure it comes out to be what we started with. And it does, right? Differentiating this, we're going to lose our 2 over 3. This is going to be lowered by 1. And we're going to have the derivative of this outside, right? And our c is going to disappear. So it comes back to what we started with. So it does in fact work. This is the answer. But just checking really quick, they use the general power rule. They said, think of this term as u raised to the n. Think of this term as du dx. And then leave dx as it is. Using the general power rule, you can solve it now. So let's check out some more problems. So this one is a little bit more, this one takes a little bit more work, is what I'm trying to say. And I'll show you why. So start off with our integral is x times the quantity 3 minus 4x squared raised to the second power dx. So there's really nothing we can do here as far as rearranging terms or making the algebra look nicer for us, right? This is already the form we want it to be in. So let's try to identify our u. Keeping with what we've been doing, let's use u to be that most interior function, right? So we're going to say u is equal to 3 minus 4x squared. So du dx is going to be negative 8x, and du is going to be negative 8x dx. Okay, so let's start plugging things in. First, let's make an observation. We can pull this x to the back. Just to group things according to what we want to do, right? So this first part is going to come out to be our u, right? It's u squared. But what we've got left now is x dx. And we want negative 8x du. So we have to do some work here really quick. We're trying to find du. What we have though is x dx, right? So how does this compare to du? This is du times negative 1 over 8, right? So another way of looking at this is to say, all right, we want this. How can we rearrange these so that we have x dx? Make sense what I mean? So what we have is negative 1 over 8 du is equal to x dx. So we come over here, we rewrite this as negative 1 over 8 dx. I mean du, my mistake. Well, now we can pull that negative 1 over 8 outside. I'm going to erase this for room. So this is going to come out to be negative 1 over 8 times 1 over 3 x cubed plus a constant. Simplifying, this is going to come out to be negative 1 over 8 times 3. It's going to be 24, right? 24. My mistake, I meant to write u here, not x. U cubed plus c. Now we're going to substitute our u back in. When we do that, we're going to get 1 over 24 times 3 minus 4x squared plus c. I forgot the cubed. Now, if we took the derivative of this thing to check, should come out to be the same. Checking our work, though, comparing to what the book has done, they started by saying, hey, this du dx is going to be negative 8 over x. Comparing that to what we have, if we multiply negative 8 over x dx by negative 1 over 8, we have our original integrand. Make sense? Folks at home, does that make sense to y'all?
Yes.
Yes, awesome, cool. So pulling out that factor of negative 1 over 8, they then applied the general power rule, and they simplified. So again, the general power rule is just a special case of u substitution. This, while quicker, sure, because it's a general rule, will require you over time to remember more rules than if you understand the u sub method. And that's why I'm trying to juxtaposition the two against each other, right? That way we can see what the general power rule actually is compared to what u substitution as a method is. Cool? Now jumping to the next problem. It's almost identical actually to what we just did. Almost identical. Except instead of an x, they have a negative 8. And what they're trying to say here is we can't think of this as pulling 1 over x outside of the integral and doing that same thing as we did last time. That the general power rule kind of leads us down this dark alleyway, if you will, that makes us open for mistakes. That instead, in this case, what we would want to do is try to expand our integrand and then integrate. So going through and actually doing the algebra here, you get this huge long polynomial, right? And then you would want to integrate. So this is just kind of a warning, if you will, of what to look out for. Just because it looks like general power rule doesn't mean it necessarily will be. A lot of integrations, might look the same, but are not. So, as another example, think I'll let y'all work on this one on your own. I'll give y'all about 3 minutes to get it done. And then I'll do it up on the board here. For those at home, this is slide 50. Slide 50 for week 10 notes. You can find it under exam 3 on Blackboard. So are you in this problem? It's going to be x cubed plus 1, right? So du dx, that's going to be 3x squared. And du is going to be 3x squared dx.
Why is it 3x squared?
Taking the derivative.
Okay, yeah, no, that makes sense.
So right on the first little bit of this, pretty straightforward, right? We're just going to rewrite this as u to the 1/2. Well, we've got 7x squared. We want 3x squared. So we can break up this 7, right? This factor of 7. We can break it up as 7 over 3 times, let me write it a slightly different way. We've got 7x squared dx. We can rewrite this as 7 over 3 times 3x squared dx. So this thing is going to be like 7 over 3 du. Agreed? So now when we put all of this together, we're going to get u to the 1/2 times 7 over 3 du. We can pull out that 7 over 3. and multiply it by the integral of u to the 1/2 du. This is going to come out to be 7/3 times 2/3 u to the 3/2 plus c, right? So now substituting everything back in, we get 7/3 times 2/3 times the quantity x cubed plus 1 raised to 3/2 all plus c. We can reduce this now, simplify it a little bit to get 14/9 times x cubed plus 1 raised to the 3/2 plus c. In comparing our answers, they went ahead and grouped things kind of the same way, right? But they pulled out that 7/3 and then applied the general power rule. And after that, they simplified and got the same answer. So sometimes these methods are going to require you to massage the algebra just a little bit. It's going to require you to notice things like this, right? And to think ahead. That's really what it's going to ask you to do. Think ahead and look at what you're going to need. So again, this general power rule is just an application of what's called substitution or U sub. All right, so in this case, we want to integrate (1 minus 3x raised to the 1/2 power dx. Can't quite do that though, can we? We need to use U sub here. So we're going to choose 1 minus 3x to be our u. So du dx is going to be -3, and du is going to be -3 dx. But we don't have a -3 dx here. But what we could do is we could rewrite this as -1/3 times 1 minus 3x 1/2 -3 dx. Same exact thing, right? When we move that -1/3 inside, these things are going to cancel to give us 1. So we've done nothing here. Absolutely nothing to the algebra. We just rewrote 1 as -1/3 times -3. Now, this tells us with U sub we have negative 1 over 3 times u to the 1/2 du. Integrating this out, negative 1 over 3. This is going to give us 2 over 3 u to the 3 over 2, that quantity plus c. Let's simplify everything. It's going to give us negative 2 over 9 u raised to the 3 over 2 plus c. And now we can substitute our u back in. When we do, we get negative 2 over 9 times the quantity 1 minus 3x raised to the 3 over 2 power plus c. So let's compare our answers really quick. They do the exact same thing, don't they? They say, hey, looking up at the very top, they have all the notes about the u sub written. Say, hey, if you set u equal to 1 minus 3x, du dx then is negative 3, and du is negative 3 dx. So now we can rewrite our original integral in terms of u. When we do that, we can integrate, simplify, and then substitute u back in. So as a general practice, the best way of going about this is you want to pick some part of your integrand that's most interior, typically speaking, right? Like this. Doing that, you're gonna say, all right, this thing's u, get the derivative, find the differential. Excuse me. Rewrite your integral with u sub, integrate that thing, and then substitute whatever u is back in. That's the practice here. And that's all they're trying to say with this guideline. So I keep calling it u substitution or u sub. Your book calls it substitution. It's, if you Google this, and I suspect many of y'all will, and I actually would like many of y'all too, because it's a good practice to Google things. It's more commonly known as u sub. Where it comes from is the chain rule. When we take the derivative of the composition of two functions, what we end up with is the derivative of the exterior function with the interior intact times the derivative of the interior function. So it comes out to be like this, right? So if we're going to move backwards and integrate with respect to x, that's where u sub comes in. U sub just says, hey, this interior piece, you can think of it as a constant compared to du dx times the differential dx. It's a constant in the sense that this will reduce to du, and that will become your interior constant. That's really what they're trying to say. Because what the chain rule does Well, let's step back even further. What the derivative does is it compares the rate of change of your function against a variable, right? So your derivative is really just the rate of change of your function as x changes, right? So if we have something like this, what we're really saying here is that g changes at a particular rate with respect to our function ux, and ux changes at a particular rate compared to x. So in that way, it's really just a daisy chain of related rates. Make sense what I mean? So what u substitution is doing is saying, hey, if that's the case, then to get back to where we're originally going, I can kind of think of this interior function as a constant, so long as I can rewrite our differential dx in terms of du. Does that make sense what I mean? So having said that, it's really what, like I said, the antiderivative is doing with u sub. So now, jumping to another example. If we want to integrate this, what's our u going to be? People at home, what do y'all think? We want to integrate x times the square root of x squared minus 1 dx. What is our u going to be here?
X squared minus 1.
Yeah, absolutely. U is going to be x squared minus 1. Now, before we go any further, let's really quickly rewrite this, just so that it looks nicer. This can be rewritten as x times the quantity x squared minus 1 raised to the 1/2 power dx. So then, coming back now to u, du dx, this is going to evaluate out to be just 2x. So du is going to evaluate out to be 2x dx. So now substituting u in, we're going to run into a problem, aren't we? We only have the x here. We don't have the 2. So if we multiply by 2 and divide by 1/2, we can get everything inside, right? So what I mean to say is we can rewrite this thing move this x over so that it looks like this. This 1/2 and this 2 is going to cancel, it'll be 1, right? So We've only multiplied all of our integrand by 1. Doesn't change anything. But now we have our du. So we can pull out that 1/2. To get, this comes out to be u to the 1/2 du. They really like that form. So I'm going to jump to the next slide just to compare everything. Notice they used that trick. They multiplied and divided by 2, just so that we could get that 2x in there, because we had to get it in there somehow, right? So multiplying by 1 and dividing that same value out, right? We get the 2 divided by 2, it's multiplying by 1. Gives us our 2x, and now we can rewrite it in terms of du. From there, we apply the power rule, simplify, and substitute u back in. And of course, we can double check by differentiating, just like they point out. Comes out to be the same thing. So just some more details on vocab. In particular, with this problem, what we're going to want to do is integrate, right? We're going to want to integrate dq dx. And this idea of propensity to consume, it's the rate of change of consumption with respect to the income is called the marginal propensity to consume. And that's what this thing is measuring. That's what this dq dx is. So if Q is going to be the income consumed, how are we going to solve for Q here based on everything we're given? We're just going to integrate, right? Integrate with respect to X. So what is that going to look like? Okay, let me go about this problem slightly different. This is actually two problems in one. They want us to use the initial data that at 2005, are they measuring years? As yeah, okay. Yep. 33,000 and DQ told is 0.98 times X minus 1999 all raised to the negative 0.02 power. Really quick, it's going to be convenient for us to rewrite that decimal power as a fraction. So let's go ahead and just do that now. Since 0.02 is equal to 2 over 100, you can rewrite this as 2 over 100. Just makes it that much easier for us to deal with down the road. So we want to integrate this. What are we going to do here? We're going to go about this.
Make x minus 19,199 your u.
Okay. So if we do that, then our du is going to be 1, right? And dx, or du dx is going to be 1, and du is going to be just dx. So really quickly, I want to just jump to the next slide to show this entire process. What they're going to do, they're going to rewrite it this way. You don't actually have to use u sub. It looks like a u sub problem because it's so intense, right? But we don't necessarily have to write it that way. That said, I think you're right, u sub is the better way of going about this because it's going to just make it that much easier for us to deal with. So using u, the point of using u sub here is just to make the math prettier for us. Right? So if that's the case, then what we're going to end up with is, let me use green again, 0.09 minus 6, excuse me, 0.98 integrating u to the negative 2 over 100 du. Well, we apply the power rule. We get, this comes out to be 0.98 times 1 over negative 2 divided by 100 plus 1 times u to the negative 2 over 100 plus 1 all plus c, right? Everybody agree? So this is going to come out to be, here, we're going to end up with 98 over 100. Agreed? So this is going to give us 0.98 divided by 100 over 98 times u to the 98 divided by 100 all plus c. These are going to cancel. So we have just u to the 98 over 100 plus c. Make sense what I mean? And that's kind of their point here, is that in this case, if you really wanted to, you could just apply general power rule and make it a little bit easier if you wanted to take that shortcut. knowing the general power rule, or we could go the U sub route. And that's what I was trying to say before. Does that make sense what I mean? So now, from here, we're going to plug in our initial condition and solve the rest of this problem. We're going to say, all right, cool. Now that we know the general form of our function, once we substitute u back in, then we're going to sub 2005, and for x, set that thing equal to 33,000 and solve for c. So all of this, based on what we've just done here, u of x minus a q of x is going to be x minus 19,999 raised to the 98 over 100 plus a constant. But we know that this thing at 2005 so 2005 minus 19,999 raised to the 98 over 100 plus c. This thing's going to be equal to 33,000. Using this data, we can now solve for c and get the exact form. That's what they've done here. And then from there, they went back to the original question and asked, would the family have saved more than $30,000? Consumed more, I mean to say. So with that, getting into section 5.3 now. 5.3 is going to be all about integration with logarithms and exponentials. So we know that the derivative of e to the x is just equal to e to the x. So when we integrate e to the x, since we're undoing this derivative, it's going to get e to the x plus a constant. That's where this first simple exponential rule is coming from. But that said, the general exponential rule, it's just u sub, but with exponentials. Since, I'm going to write it here actually. Since the derivative of this thing comes out to be e to the ux du dx, using u substitution, we get the general exponential rule. And that's all they're doing here. Does that make sense to everybody? Let's look at a few of these. Start off with, we've got, let's look at A. I think that'll be a good one to start off with. We've got the integral of 2 e to the x dx. Well, we can rewrite this as 2 the integral of e to the x dx. We just saw that this thing comes out to be 2e to the x plus c, right? Now let's compare that to b here. Notice what we've got is e raised to some u. Agreed? So using u sub, setting u equal to 2x, du dx is going to come out to be 2. So du is going to come out to be 2 dx. By substitution, this thing comes out to be e to the u du. Which is just equal to e to the u plus c. So when we integrate all of this, then substitute u back in, we get that e 2x dx has to be equal to e to 2x plus a constant. And all I've done here is said, all right, given that this comes out to integrate using u sub as e to the u plus c, plugging 2x back in for u, we get our solution. Now what about c? Let me give you all about a minute to work, give you all 2 minutes to work on c really quick. Did anybody get e to the x plus 1/2 x squared plus c? The way we're going to go about this, we're going to use that sum and difference rule. Write this up as the integral e to the x dx plus the integral x dx. This thing's going to evaluate out to be e to the x. This thing's going to evaluate out to be 1/2 x squared. All of that plus some constant. So let's check out these answers. I almost dropped my chalk. All right, so in the case of number 2, or I mean of A, We just pulled out that 2, right? And integrated e to the x dx as if it was just e to the x dx. So that gave us 2 e to the x plus c. In the case of b, we used u sub and got e to the 2x plus c. In the case of c, we used the sum and difference rule. And as always, go ahead and differentiate to check your work. It's a good idea. All right, so this one's a bit more involved as a whole, isn't it? Here we're looking at integrating e to the 3x plus 1. All right, right away we know what our u is, right? Our u is going to be 3x plus 1. So our du dx is going to come out to be just 3. And our du is going to come out to be 3 dx. We don't have a 3 dx here, but we can multiply it by 1 and force it to come out, right? We can rewrite this as e 3x plus 1 times 1 over 3 times 3 dx. That's going to give us 1 over 3 e to the 3x plus 1 3 dx. Substituting now. We're going to get 1 over 3, the integral e to the 3x plus 1, or my mistake, e to the u du. This is just going to come out to be 1 over 3 e to the u plus a constant. So substituting back in, we get that the integral is equal to 1 over 3 e to the 3x plus 1, all that plus a constant. And if we differentiated that, the derivative of our exponent would cancel with that 1 over 3, wouldn't it? So we're just going to get e to the 3x plus 1. Checking our work really quick. Using u sub. We're going to get the exact same answer. Okay. So this one was a little straightforward, by and by. But this example, now we've got 5x out front. And e is raised to a negative exponent. we've got 5x e to the negative x squared. Let's set u equal to negative x squared. Let's change du dx equal to, taking the derivative up top, you get negative 2x. So du is going to be equal to negative 2x dx. That's not what we've got, is it? The easiest way, I think, to handle this would be just to inject a 1 in here, right? To rewrite this as 5x e, let's actually pull that 5 outside, e to the negative x squared, negative 1/2 times negative 2 x dx. Now we can pull that negative 1/2 outside to get negative 5/2, the integral of e to the negative x squared, negative 2x dx. Now we can apply u sub. When we do, we get negative 5/2, the integral of e to the u du. This is going to come out to be negative 5/2 e to the u plus c. So substituting everything back in, we get negative 5/2 e to the negative x squared plus c. Comparing our work, same idea. Inject that 1, right? That way we can break up the integrand in terms of e to the u and du. And then just apply the general exponential rule. Makes sense to everybody? Again, this is just u substitution, through and through and through. That's a lot of these integrations. That said, fun fact, that integral can't be solved. There's actually a bunch of integrations that can't be solved. That one, there's a trick where you can solve it, but you can't solve it directly. So it's not the case that every function or every integrand can actually be integrated with the methods that we know. And that's true at every level of mathematics. There are some problems we just can't actually solve using integration. And it's become a real headache in a lot of cases. Having said that, natural logs. So remember, in the past, we had the simple power rule, which came out to be this, right? So n plus 1 plus a constant with the rule that n cannot be equal to negative 1. This is why. The integral of 1 over x dx is equal to the natural log of the absolute value of x. Now, this is another easy mistake to make. Everybody does it. I actually caught a mistake on a paper that I was reading not too long ago where the guy forgot to use the absolute values. Everyone does that mistake. It's just something that happens. So the reason why in the simple power rule, n can't be equal to -1, because that integrates out to be the natural log. And this makes sense when we think about the derivative of the natural log, right? This came out to be 1 over x. So the reason why the integrand of 1 over x dx is the natural log is because the derivative of the natural log is 1 over x. And this absolute value is just playing the role of making sure our natural log never drops below 0. And that makes sense just looking at what it represents, right? So the absolute value of x as a graph looks like this. So the ln of x, the absolute value of x, should look like this. My mistake. I meant to not write 1 over x here. I meant to write absolute value of x. I apologize about that. Meanwhile, one over x that thing looks like this. So just to kind of give some intuition, we can look at the graphs and kind of intuit why that absolute value is there, right? So having said that, let's jump to the next slides. I would like for y'all to try to really quickly work on A. I'm going to do B and C up here on the board. So for number A, who got 4 times the ln of the absolute value of x plus c? Cool. So looking at these, you can pull out that 4 right away. That's the constant multiple rule. And then we apply the simple logarithmic rule. In the case of B, use u sub, set u equal to x squared, set du dx equal to 2x, apply the general logarithmic rule, and then substitute u back in. Now, just a note on this. Did they have to keep the absolute value here? People at home, what do you think? Do we absolutely have to, in this particular example, have the absolute value sign? No, and the reason why is that the only rules we have about logarithms is that we can't pass a negative value through to them. Well, the last time I checked, x squared is always positive. So I really don't need to worry about, in this particular case, the absolute value sign. It's good to have, it's good practice, but just to compare the answers, the reason why they're able to drop it off in the book is because x squared is always positive. Now, really quickly, looking at the last example, again, u sub. Once we get it to this point, we can apply that general logarithmic rule, which is really just the simple logarithmic rule. They just like to say du dx times dx. Excuse me. And then once we do, we get the ln of the absolute value of 3x plus 1 plus c. All right, last example. How are we going to do this? We're going to apply the same trick we've been applying, multiply by 1. That is a mathematician's favorite. So this thing's going to be 1 over 2x plus 1, my mistake, minus 1 dx. We're going to say, let's use 2x minus 1 to be u, then du dx, that thing's going to be 2, and du is going to be 2 dx. Okay, now, we're going to have to multiply, like I said, by 1 here. When we do that, we have 1/2 times 2 over 2x minus 1 dx. And we can pull out that 1/2. And we get 2 dx over 2x minus 1. So just a note, there's 2 different ways that fractions will oftentimes show up in the notation. We can use dx outside of the fraction, or we can pull it up in the numerator. It's really a matter of preference. But from here, now we can rewrite this as 1/2 the integral of du over u for 1/2 the ln of the absolute value of u plus c. So substituting back in now, we get 1/2 the ln of the absolute value of 2x minus 1 plus c. Comparing answers. We do the same thing. You use u sub, just like you see in that top line. We multiply by 1 so that they can get that 1/2 and that 2 in there, right? They really just get that 2 in there. Then they use u sub, integrated, and then substitute it back in. Having said that, it is a minute after, so I will let y'all go. If y'all have any questions, I'll stick around.